picture the surface of the ocean, we imagine a perfectly smooth, uniform curve wrapping around the globe. But if you strip away the tides and weather to measure only the surface shaped by Earth's gravity, you get the geoid. It is an equipotential surface, and it is entirely uneven. This EGM 2008 geoid map shows a depression south of the Indian Peninsula, where the sea level sits exactly 106 meters below the global mean. This Indian Ocean Geoid Low covers over 3 million square kilometers, a footprint roughly the size of the Indian subcontinent. A surface dip of this magnitude mathematically dictates a massive, uncompensated mass deficit in the subsurface. The local gravitational pull here is measurably weaker, meaning there is significantly less physical matter beneath this patch of ocean than the global average. Historical models attempted to explain this void through isolated features, such as an unusually thin crust or a single slab graveyard in the mantle. However, these individual mechanisms fail to account for the total missing mass required to cause a 106-meter drop. The math only balances when we apply the superposition thesis. This suggests the geoid low is an interference pattern, the result of multiple high and low density forces acting simultaneously across the entire vertical column of the Earth. To resolve this, we cannot look at a single depth. We must sequentially deconstruct the Earth's interior from the crust down to the core. Proving these deep Earth dynamics has long been stalled by a lack of high-resolution seismological data from the deep oceanic basins. Most of our seismic networks are land-based, leaving the ocean floor structurally opaque. Between 2015 and 2020, India's Ministry of Earth Sciences deployed an extensive array of ocean bottom seismometers, or OBS, directly into the anomaly. The mission utilized two distinct configurations. Active OBS transects profiled the shallow crustal structure using high-frequency signals, while a passive linear array of 17 broadband stations targeted the deep mantle. These passive sensors sat on the seafloor for 28 continuous months, recording low-frequency, stochastic seismic noise from teleseismic events. By capturing waves from distant earthquakes that traveled through the deep mantle, the sensors turned the Earth's natural seismic background into a probe. Because this data is buried in the chaos of the ocean, researchers use data-adaptive polarization algorithms to filter the signal. This allowed them to isolate clear wave faces from the interference of currents and marine life. This high-resolution dataset provided the first direct thermodynamic evidence needed to validate the superposition thesis. Layer 1 of our deconstruction is the oceanic crust and lithosphere along the 10-degree north latitude profile. Wide-angle reflection and refraction seismic profiles allow us to map the precise thickness of this boundary. On the western edge, beneath the Comorin Ridge, researchers found a localized zone of thickened crust, reaching 14 kilometers. This is the result of magmatic underplating. When India broke from Madagascar 90 million years ago, intense plume-ridge interactions produced an excess of melt that solidified against the bottom of the crust. However, as the profile moves east toward the center of the geoid low, this anomaly thins out into completely standard oceanic crust. Using 3D constrained potential field modeling, we can calculate the exact gravitational contribution of this topmost layer. The math reveals a limit. The crust and uppermost mantle structure can only account for roughly 10% of the total geoid deficit. The crust's limited impact on the geoid confirms that the primary source of the deficit resides within the deeper mantle structure. Moving down the column, we enter the upper mantle, specifically the depth range between 80 and 280 kilometers. To map this region, geophysicists utilized Rayleigh wave phase velocity inversions to construct 1D velocity depth models. By tracking how long it takes Rayleigh waves in the 15 to 197 second period range to travel through this zone, researchers can determine density. As a rule of thumb, slower waves indicate lower density material. The models show the lithosphere directly beneath the geoid low thinning from 75 kilometers to just 47. Beneath this thinned boundary lies an incredibly thick low-velocity zone, or LVZ. Slow shear wave velocities in this region indicate a hot, partially melted, low-density environment. This pocket of superheated material provides a massive negative density pull, acting as the first major structural driver of the surface gravity deficit. To find the source of this heat, we look deeper into the mantle transition zone, specifically the D410 and D660 phase boundaries. Because this zone sits hundreds of kilometers deep, researchers mapped it using P to S radial receiver functions from teleseismic earthquakes. The mapping reveals an 800-kilometer-wide physical depression in both the D410 and D660 boundaries at the geoid center. Mineral physics tells us that extreme heat is forcing the natural transition of majorite garnet into perovskite to occur significantly deeper than usual. To cause this level of downward deflection at the D660 boundary, the excess temperature of the rising rock must exceed 1,000 Kelvin. This intense thermal deformation is the signature of a massive, buoyant mantle superplume punching upward toward the crust. To find the ultimate origin of this heat, we look to the core mantle boundary. Millions of years ago, as India drifted away from Gondwana, the ancient Tethys oceanic lithosphere detached and began sinking. This high-density slab has spent eons descending through the lower mantle. Resting on the core mantle boundary is the African large low-velocity province, a volatile structure also known as the African superplume. As the cold Tethys slab reaches the bottom, its mass churns and displaces the edge of the African superplume. This lateral displacement forces superheated low-density material to flow eastward and erupt upward directly beneath the Indian Ocean. This completes the superposition. The IOGL is formed by positive high-density mass at the bottom, interacting with negative low-density plumes rising at the top. Stacking the crust, the low-velocity zone, and deep mantle upwellings aligns the mathematical components. The high-density Tethys slab creates a positive geoid force. Subtracting the density deficits of the hot upper mantle pulls the total back down, precisely equaling the 106-meter surface deficit. This geoid low is a dynamic interference pattern, the product of a 20-million-year-old tug-of-war between sinking ancient oceans and rising superplumes. In geophysics, researchers must account for the non-uniqueness problem. Multiple, often contradictory models of the mantle can mathematically predict the same surface geoid low. Only the direct physical deployment of the OBS arrays on the seafloor provided the tie-breaking evidence needed to map the actual thermal engine. Resolving planetary scale mysteries requires moving past mathematical speculation in favor of relentless, long-term deep ocean observation.